So quick review. So suppose we had a planet whose axis was oriented perpendicular to the incoming light source. What does that look like? Well, in every latitude circle, we're going to have half in the light and half in the dark. And so it's going to be 12 hours of light, 12 hours of dark everywhere. So the day length is the same everywhere. On the other hand, our surfaces are going to be more perpendicular at the equator, and then they're going to get rotated away less perpendicular as you go away from the equator. So the conclusion is that you're going to get more insolation than at the tropics because of the orientation, and less insolation as you go towards higher or more southern latitudes. So, as a result, we're going to expect the tropics to generally be warmer because it gets more insolation, and higher latitudes are going to be generally colder. So if the planet was oriented straight up and down, we would just have warm tropics, we would have colder poles, and that would be the whole story. Now, if we tilt the planet instead towards the sun, then we went through this argument last time that argued that the hemisphere that gets tilted towards the sun is going to get more insolation because the surfaces orient themselves a little bit more perpendicular, and also because you have more time in the day, more time in the light, and less time in the dark. And it's exactly the opposite for the hemisphere that gets tilted away. That gets less insolation. Conclusion: the hemisphere that's tilted towards the sun, towards the light source, is generally going to be warmer because it gets more insolation, while the hemisphere tilted away from the light source is generally going to be colder because it's getting less insolation. Okay, so what's this got to do with the seasons? How do we put this together to explain the seasons? Well, the basic idea is like this, that the Earth goes around the sun in its orbit. Now, this is my attempt, of course, to draw a 3D figure on a 2D page, which, of course, is always hard to do. But you can kind of think of this as being sort of on the table in front of you, and we're looking at it sort of on a view, from above and standing behind, looking down at this thing going around in a circle on the table in front of you. And the way this works then is that this axis, the axis of rotation of the Earth, is tilted. It's tilted by 23 degrees. It's tilted with respect to the perpendicular to your table. So instead of being exactly perpendicular to the table, it's tilted by 23 degrees. And notice that the sense of the tilt is always the same, right? It doesn't change the sense of the tilt as it goes around on its path. If it's tilted this way, it's sort of this way relative to the table. When it goes along its path, the only thing that changes is the position of the object. The tilt stays the same. It's still tilted the same way. And then just changes its position, but the tilt is still the same way. So it's always tilted in the same direction relative to the table as it goes around the sun. Okay, if that's the case, then clearly there are going to be points in the orbit where the northern hemisphere then is going to be tilted such that it's pointing towards the sun, or at least as close to pointing towards the sun as it can be. And then as it goes around on its path, the tilt stays the same, but its position changes. So when it gets to here, well, now it's not really pointed towards the sun or away from the sun, right? It's sort of tilted towards the side. And then as you get along to the other side of the orbit, now the tilt stayed the same, but the position changed. And now all of a sudden, the northern hemisphere is tilted away from the sun. And so forth and so on. Now, we know from last time that when the northern hemisphere ends up being tilted towards the sun, then the northern hemisphere is going to get more insolation. And getting more insolation means that it's going to be warmer. So over here, the northern hemisphere is going to be warmer. And by contrast, when we're on the other side of the orbit and the northern hemisphere is tilted away from the sun, in this case, the northern hemisphere gets less insolation, it's tilted away, And so as a result, the northern hemisphere is going to be colder on this side. And so that's basically the seasons. Over here on the side where we're tilted towards the sun, as we go around, we're getting more insolation. That's summer. And on the other side, when we're tilted away, less insolation, that's winter. That's basically how it works. And then in between, we're not tilted towards or away. So those are our in-between seasons, our spring and our fall. We're sort of just tilted towards the side in this case. This is the book's representation of the same kind of thing. So you've got your planet going around the sun. The tilt stays the same as it goes around, just changes its position. And so on this side over here, the northern hemisphere is tilted towards the sun, so it's warmer. And then on the other side, it's tilted away, so it's colder. That's winter. And then in between, it's just tilted towards to the side. Now, it's worth thinking about this in-between case just a little bit. So if you think about this, if you initially had an object whose axis was straight up and down, so that the latitude circles were half in the light and half in the dark, and you took that guy, so let's say that you've got a ball in your hand, and the axis is straight up and down, and somebody's shining a light at that ball, and you take it and you just sort of twist your wrist a little bit, so it's not tilting towards or away, it's just tilting towards the side. The end result's going to be that you're not going to change the day length, right? All you did was tilt it towards the side. And so each of those latitude circles are still going to be 12 hours in the light and 12 hours in the dark, right? And if you think, so another way to say the same thing is that the light-dark line, the line that separates day and night, passes through the poles when you had it straight up and down. And if you just tilt it towards the side, it's still going to pass through the poles. All you did was sort of tilt it towards the side so that now it's sort of inclined a little bit, but it's still 12 hours in the light and 12 hours in the dark. I guess another way to say the same thing is that when you sort of just tilted this to the side, you took the pole and you moved it along the light-dark line, right? The day-light line. So the poles are still passing through the day-night line, and as a result, it's still 12 hours in the light, 12 hours in the dark on each circle. I'll let you guys sort of think about that for a while, but that's how it works. Okay, so it's worth actually putting some dates and names on here to have reference points, sort of for the trip around the circle, a trip around the sun. So these guys have names. So this point over here, we're the northern hemisphere. So we're going to do this from a northern hemisphere perspective, and then I'll bring up the southern hemisphere in a second. But this point over here, where the northern hemisphere is pointed as close to being directly to the sun as it gets, this point over here is called, where you're pointed directly towards the sun, we'll say, it's called the summer solstice. The summer solstice, that's when we're pointed directly towards the sun. And for the northern hemisphere, that happens on June 21st. June 21st, that's when we're pointed directly towards the sun. And so as a result, that's going to be the day we get the most insolation. It's also going to be the day that we have our longest day length. We spend the most days, the most hours in the light and the fewest in the dark on June 21st, because that's when we're tilted most directly towards the sun. If we go around to the other side, when we're tilted away from the sun, the point in the trip when we're tilted directly away from the sun is called the winter solstice. And by tilting away from the sun, we get our minimum insolation on the winter solstice. This is going to happen on December 21st, 6 months later. So on the December 21st, we get our minimum insolation, and we also have our shortest day length because we're tilted away from the sun. These points in between also have names here. And the names for these guys come from the fact that they still have at every point on the Earth's surface 12 hours of light and 12 hours of dark. And so the names that we give them are called equinoxes. They're called equinoxes. This word equinox means 12 hours day, 12 hours night, and that's going to be true at every latitude circle because we're not tilted towards or away, we're just tilted towards the side. So the first equinox is the one going from summer towards winter, and summer towards winter is going to be the fall equinox. The fall equinox happens on September 22nd. September 22nd. And then the second equinox, again, just not tilted towards or away, just tilted towards the side. This guy is going to happen. So this one is going from winter into summer. Winter into summer is going to be spring. That's going to be our spring equinox. Winter, spring, summer. And so the spring equinox is going to happen on March 20th. March 20th. So roughly 3 months in between the winter and summer solstices. So again, just to make sure we've got them in order, we go summer into fall, fall into winter, winter into spring, and spring back into summer. So that's basically how it works then. And so the summary statement to all of this is that the Earth's seasons, the seasons on the Earth, are just a direct result of the Earth's tilt. So they're caused by the Earth's tilt and the associated changes in insolation over the course of the year. The seasons are caused by the Earth's tilt and the associated changes in insolation over the course of the year. It's probably worth thinking just for a second what would happen if the Earth were not tilted. That is, if you had this thing going around on the table in front of you and the axis was actually perpendicular to the table. You can probably convince yourself that if that were the case, then every point in the orbit would be exactly the same. The axis would be exactly perpendicular. Each latitude circle would be 12 hours in the light and 12 hours in the dark, and you get the same amount of insolation throughout the whole year. So in that case, we wouldn't have any seasons. So the thing that's causing the seasons is the fact that it's tilted, and sometimes it's tilted towards the light source, sometimes it's tilted away from the light source. Now, the second thing I'll bring up is that sometimes when you ask people who haven't thought about the seasons before, what causes the seasons, they'll suggest that it has to do with distance from the sun, right? You're closer to the sun in summer, and you're further from the sun in the winter. And that actually is true. It's not actually true as stated, but it is true that sometimes you're closer to the sun and sometimes further from the sun. But that turns out to be a minor effect. The difference isn't really that big, and it's not going to be big enough to actually, overpower the effect of the tilt. It's really the tilt that's causing this. And to just sort of emphasize that point, I'll note that the point along the orbit when we're closest to the sun actually happens in our winter. So we're closest to the sun or in our winter. It's sometime in January, if I remember right. Whereas we're further from the sun in our summer. So the effect of distance from the sun is actually much smaller than the effect of the tilt. The tilt sort of overwhelms the fact that we're further from the sun in the summer. Okay, and then finally, if you go and you do the same kind of thing for the southern hemisphere, it's just going to be exactly the opposite. When the northern hemisphere is tilted towards the sun, the southern hemisphere is tilted away, and so that's going to be winter for the southern hemisphere. So right now, we're in summer, and so in our summer, we're in the southern summer hemisphere. That's going to be winter in South America, say, or in Australia, or in South Africa, or in most of Africa. And you go around to the other side, and when we are tilted away from the sun, the southern hemisphere is tilted towards the sun. So our winter is going to be their summer. So everything's just going to be exactly reversed. And then, of course, you just fill in your spring and your fall. So going from winter to summer is spring. So again, it's backwards from the northern hemisphere, and going from summer into winter is fall. So you just take all of your solstices and equinoxes, and reverse them for the southern hemisphere. Okay, so that's almost how it works. This does actually raise one sort of interesting question. And this is usually a point where I would do a little Atmo 201 theater in class and have a volunteer from the audience read their lines. But I guess in this case, I guess you're going to have to be the volunteer. So go ahead and read what it says up here on the top, and then we'll keep going. Read it with attitude. So put some more emphasis on this, but in my world part. That's what I'm after there, that kind of attitude. Okay, so what do I say to that? What do I say to that? Well, I'd say it's actually a good point, right? So the point that's being made here is that we said that the maximum insolation occurs on June 21st, which is the summer solstice. That's when we're tilted directly towards the sun. And that's true. That is our maximum insolation. But if you look at the temperatures, that's not when it's warmest. It's actually warmest sometime later in July and August. So just to illustrate that, I've got the temperatures for College Station, the average temperatures plotted over the course of the year here. And our maximum insolation occurs here in June. And June, if I'm reading this right, has a monthly mean temperature of 92, whereas when you get into July and August, it becomes 95 and 96. So our maximum temperature here is sort of right at the end of July, beginning of August, which is a good 5 weeks or so, 5 to 6 weeks after the solstice. So what's going on? Well, that has to do with something called seasonal lag. Seasonal lag, which is just the idea that the temperatures take a while to respond to the insolation, for reasons I'm going to explain here in a second. And scene. So seasonal lag, how does this work? Well, the thing to keep in mind when thinking about seasonal lag is that the temperature trend doesn't really depend strictly on the insolation. It actually depends on the budget. So the basic idea, the mantra, is going to be, as long as we're gaining energy, as long as we have a net input of energy into the system, temperatures will increase. That's sort of the mantra. If we're gaining energy, temperatures go up. Another way to say the same thing is as long as the incoming shortwave from the sun exceeds the outgoing IR, as long as the incoming shortwave is exceeding the outgoing IR, we'll be gaining energy. And if we're gaining energy, temperatures will increase. That's our mantra. As long as the incoming shortwave wins, as long as it's exceeding what's going out, then we gain energy, and if we gain energy, temperatures are going up. Well, if we think about the summer solstice, what's going on at the summer solstice? So here we've got our surface down here, and let's sketch in the atmosphere here. So let's just say there's some arbitrary top to the atmosphere, so there's some layer we'll call the atmosphere. And there's energy coming into the system from the sun. So that's our incoming visible. And at the summer solstice, we actually have our maximum incoming energy from the sun, right? Our summer solstice, June 21st. So what we're sketching here again was the summer solstice. And on the summer solstice, June 21st, is when we get our maximum input from the sun, maximum insolation. So if there's going to be any time during the course of the year when you would expect the incoming visible or the incoming shortwave to exceed what's going out, it would have to be the summer solstice, right? I mean, that's when you're getting your maximum input from the sun. So surely if there is a time where that's exceeding what's going out, it's going to be at the solstice. And in fact, that is what happens. At the solstice, what's going out is less. Say it's 2. So this is the kind of situation then that you might see at the summer solstice. You've got your maximum incoming energy from the sun, and that exceeds what you're radiating away. And so as a result, if you think about the net budget, you're gaining energy. At the summer solstice, you're gaining energy. And according to our mantra, if we're gaining energy, then the temperatures will go up. So what we've just argued then is that when we're at the summer solstice, temperatures should be increasing because we're gaining energy. And if temperatures are increasing, that's not our maximum temperature. That's not our warmest day, right? The next day is going to be warmer. And that goes on for a while after the solstice. It goes on for, in College Station at least, for 5 or 6 weeks after the solstice, where you're continuing to gain energy. You have more energy coming into the system than what's going out. And so it continues to get warmer and warmer and warmer until eventually that's not true anymore. Okay, so at the summer solstice, we're continuing to get warmer. So our warmest temperatures, we're gaining energy. So our warmest temperatures are going to be later. And so how does this work? What determines where we're going to get our maximum temperature? How much later? So, okay, this is what I just said. Incoming shortwave continues to exceed the outgoing IR for several weeks past the solstice, so it continues to get warmer. We continue to gain energy. Until what? Well, as we go past the solstice, a couple of things start to happen. The first is that temperatures are going up. Right? We just argued that temperatures continue to increase because we're gaining energy past the solstice. And we know from before that as the temperatures increase, then we radiate more energy. That's the Stefan Boltzmann law. So if I go back to my sketch, what that means is as I go past the solstice, I'm going to keep radiating more and more energy away because it's getting warmer. So the outgoing part of my budget is getting bigger. The second thing that happens is that as we go past the solstice, the incoming radiation, the incoming insolation, decreases. We had our maximum insolation at the solstice. When we go past the solstice, the incoming part decreases. So again, if I go back to my picture, that tells me that this part is getting smaller. As I go past the solstice, I'm getting less insolation from the sun. So I'm getting less from the sun. I'm radiating more away, and eventually we're going to reach a point where we're no longer gaining energy, right? Because what we're radiating away is getting bigger, what we're getting in is getting smaller. Eventually we're going to hit a point where those two cross, and eventually we're going to start losing energy because we're going to radiate more than we gain. So the point where that happens, where those two things cross, is going to be the point where the temperatures stop rising. Another way to say the same thing is that's when we have our maximum temperature, right? We're going to gain, as long as we're gaining energy, temperatures are going up. But as soon as we cross over to the point where we're losing energy from the system, then temperatures will start to drop. And so the maximum temperature happened just when we made that switch from gaining energy to losing energy. So for instance, by the time we get to late August, say, or September, we're going to be at a situation where the incoming solar radiation was decreasing, right, because we went past the solstice. The outgoing IR was getting bigger because it was getting warmer. And then eventually we crossed to where the outgoing IR was bigger than what's coming in. At that point, we start to lose energy. And as soon as we start to lose energy, it gets cooler, which means we've hit our maximum temperature at that point. Okay, so that's called seasonal lag. At the solstice is not our warmest day because we're gaining energy. Temperatures continue to increase until we switch over to where we're losing energy. Okay, so with the next screencast, then, we're going to go through and talk about the daily temperature cycle instead of the yearly temperature cycle. And we'll see that a lot of the same basic ideas that we applied to understanding the seasons will apply to the day-night temperature cycle as well.